Question 2 has a vertical circle. So in this example, there's a bucket and it's being whirled on a string in a vertical circle. So it says that the radius of the circle is 1.2 meters. So that's how long the whatever the string in the bucket is. 1.2 meters. The bucket itself has a mass of 2 kilograms, and at the lowest point, it tells us that the tension in the rope is 25 newtons. So if you were to draw a free body diagram of this bucket, there would be tension in a rope, tension, and we know it's 25 newtons. And we also know that there's a force of gravity. And that force of gravity is going to equal mg, which equals 2 times 9.8, which equals 19.6 newtons. Now, you can see with the numbers that the tension is greater than the force of gravity. And what that implies is that it is accelerating towards the center of that circle. It asks us to find the speed. So we're going to set this up the way we would set up our problems. For part A, we're going to say Fc equals the sum of the forces, which equals mv squared over r. And then in this case, the sum of the forces is not just one force, there's two. The sum is the tension and the gravity. Now, let's pay attention to our sign convention here, because one thing that makes it easier is if you take the direction towards the center of the circle to be positive, take the sort of outward direction to be negative. This will help us because it will allow us to keep our acceleration, this term mv squared over r, positive. So when our sign convention like that, we can see that tension is positive, minus, and then there's the force of gravity is in the downward direction, which is negative. So it's going to be the sum of the forces is T minus Fg, and that equals mv squared over r. So now we can start plugging in some numbers. We have 25 minus 19.6, which equals 2 v squared divided by 1.2. And I don't think I've got an answer to that, so let me quickly do that. So 25 minus 19.6 times 1.2 divided by 2. So that gives me an acceleration of, square root that. That gives me an acceleration of 1.8 meters per second. So v equals 1.8 meters per second. Don't take my word for it. You should try it yourself. And if I made a mistake, email me and I will fix it. So that's the speed of the bucket at the bottom. Okay, and we're kind of assuming that the bucket is moving at that speed. Now the part B says, how fast must the bucket move at the top of the circle so that the rope does not go slack? So let's take that bucket and put it at the top of the circle now. So if the bucket is there, the rope is now kind of holding it up there. The radius it's still 1.2 meters in radius. Now it's asking how fast must the bucket be moving so that the rope does not go slack. So this whole idea of does not go slack, what we're going to do is sort of assume that it does go slack. And when it goes slack, what that means is T equals 0, means the rope goes slack. And so what we're going to do is solve this problem for T equals 0 and then say it can't go any faster than that, or it can't go slower than that, or it won't make it around. So we're going to take T equals 0 as sort of the limiting case and then solve our problem around that. So for part B, so now if T is equal to 0, at the top, the only force acting on it is the force of gravity. Remember, that's kind of the situation with vertical circles. If you can get it to the top with a bit of tension left, the tension can drop to 0 at the very top, and then gravity acts as the force that's causing the object to stay in its circle. So in this example, problem, we've got Fc equals the sum of the forces equals mv squared over r. Let me just be explicit here. This is at the top of the loop. And then this problem is at the bottom of the loop. Okay, so then now going back to the problem, the sum of the forces at the top is just Fg, and that's going to have to equal mv squared over r, right? And this FG is equal to mg. I'm just going to write it in there. In fact, the mass doesn't count. It doesn't matter, I should say. It cancels out of the problem. And we can rearrange this equation and solve for v, and you can see that it's equal to the square root of g times r. So solving that, we get the square root of 9.8 times 1.2. So then our speed at the minimum speed at the top, or the speed at the top, 9.8 times 1.2, and we're going to take the square root of that, 3.4 meters per second. So the question is asking, how fast must the bucket move at the top so that the rope does not go slack? So at 3.4 meters per second, the rope goes slack. So what we can say here is the speed must be greater than 3.4 meters per second, or the rope will go slack. All right, I hope that makes sense.